So, we were discussing about the dimensionless form of the momentum equation, dimensionless form of the energy equation, the boundary conditions again in dimensionless forms, essentially for the case of fluid flow, the no slip velocity, and what would be the condition of velocity at a point far from the plate, such that at that point the velocity is going to be equal to the local free stream velocity outside of the boundary layer. And similarly, we are also looking at the energy equation in what would be the form of the boundary conditions. For example, what is going to be T star, that is a dimensionless temperature at any axial location, but on the plate itself. So, T star at x star comma 0, that means y star equal to 0 would be equal to 0, because of the way we have defined the dimensionless temperature T star, where T star was simply T minus T s by T infinity minus T s. So, on the plate T is equal to T s, and therefore, T star would be equal to 0. At a point far from the plate, the temperature of the fluid would simply be equal to T infinity, and the value of T star in that case would be equal to 1. So, we were looking at two equations, two governing equations for two processes, one for heat transfer and the other for momentum transfer. And we saw that the ones that separate the combination of terms that separate these two equations, that differentiates between these two equations, are the presence of similarity parameters. One is the Reynolds number for the case of momentum transfer, and the second is Reynolds times Prandtl number for the case of heat transfer. So, these are the only difference between heat transfer and momentum transfer. So, what we would like to do is we have proposed then that if we could keep the Reynolds number to be the same for heat transfer as well as for momentum transfer, and if we can choose a hypothetical fluid with a Prandtl number to be equal to 1, then these two equations, dimensionless form of these two transfer equations, are identical. And if in addition we assume that the flow is taking place over a flat plate, then the governing equation, the boundary conditions of the governing equations are also going to be identical. So, that is the case of dynamic similarity, which tells us that for a dynamic similar system, the expression of dependent variable for the case of momentum transfer, which is u star, can be replaced by the dependent variable of the other equation, which is T star, and therefore, an analogy, a similarity, an equivalence between the momentum transfer and heat transfer can be established to obtain expressions, known expressions of one dependent variable from the known expression of another dependent variable. So, we will look at that. It will be very clear towards the end of this class how it is done. So, let us look at this slide, which was the last slide of the previous class, where I have identified the governing equations, the similarity parameters, Reynolds number and Reynolds and Prandtl number. This is for momentum, this is for energy, and the boundary conditions using no slip and a point far from the flat plate. What would be the velocity condition, the temperature at y equals 0 and temperature at y equals infinity. So, with this knowledge, by keeping the Prandtl number to be equal to 1 and keeping the Reynolds number to be the same, and assuming that the flow is taking place over a flat plate, everything in this equation, between these equations and the boundary conditions are identical. So, we have a similar system, dynamically similar system. So, what we are going to do is find out what is Reynolds analogy and modified Reynolds analogy. So, for that I am going to look at the function, what could be the functional form of u star. I do not know what would be the exact form of it, but I know that if I could write the u star, if I could write the functional form of u star it should contain the independent variable x star, independent variable y star, the similarity parameter Reynolds number, and the pressure gradient present in the system, which is dp star dx star. So, my functional form of u star is going to be x star, y star, Reynolds number based on the entire length of the plate, and dp star dx star. I do not know how u is going to be connected with x, y or Reynolds number, but I know that a functional form like this would exist for the case of flow. Now, in terms of engineering interest, we would like to find out what is the shear stress at the surface. That means, at the surface, I mean at y star to be equal to 0, that is at the surface. So, which I let us say call it as tau s, the shear stress, which would be mu times del u by del y at y equals 0. So, this is the shear stress at the surface, and if I non-dimensionalize it, it is simply going to be mu v by L del u star by del y star at y star equals 0. So, that would give me the expression for shear stress, and the shear stress coefficient, we understand that by definition it is tau s by the dynamic pressure, which is half rho v square. V is the approach velocity, rho is the density. So, that is the definition of CF. So, the definition of CF, it can be written as Reynolds number for the entire length del u star by del y star at y star equals 0. This was simply obtained by putting the expression of tau s over here and absorbing this half rho v square in it to obtain 2 by REL del u star by del u star by del y star at y star equal to 0. So, this if I try to find what is the del u star functional form of del u star by del y star at y star equals 0. So, if you look at the expression, the functional form, the hypothetical functional form of u star, I am trying to find out del u star del y star at y star equal to 0. Since I am assigning a specific value of y star to be equal to 0, this must be a function of x star, dp star, dx star and Reynolds number based on length. Since I have specified the value of y star to be equal to 0, so therefore, the y star does not appear over here. Now, this is the flow, this is a flat plate over which the flow is taking place, and this side is the turbulent flow. Now, if the geometry is prescribed, then you would be able to obtain dp star dx star separately. So, this for a prescribed geometry. I will expand on it in a moment. Remember that what I have told you before is inside the boundary layer the flow is viscous, outside of the boundary layer the flow is inviscid. So, there is no effect of viscosity in here. Since you have viscosity present effect of viscosity present inside the boundary layer, you cannot use known equations which are available to give which are there to provide what is the pressure drop as a function of distance. Now, if someone tells you that what is the equation that provides the pressure drop in a flow, the name that comes to your mind is Bernoulli's equation, because Bernoulli's equation would relate the pressure gradient, the pressure head, the velocity head and the gravity head. Now, if I assume the plate to be horizontal, which is the case in this case, so therefore, it is going to be the summation of pressure head and velocity head to be constant. So, if I know the velocity, or I can express the change in pressure in terms of change in velocity head, that is what Bernoulli's equation is all about. Now, there is a catch though. The Bernoulli's equation is strictly valid for inviscid flow, for flow where the effect of viscosity is absent. So, inside the boundary layer, technically I cannot use Bernoulli's equation as the flow is viscous there. So, the solution, but the observation is outside of the boundary layer the flow is inviscid. So, if the geometry is known to me, then I would be able to use Bernoulli's equation in the flow domain outside of the boundary layer to obtain an expression for dp dx or dp star dx star independent of everything. So, if someone gives me the geometry, I should be able to obtain what is dp star dx star outside of the boundary layer through the use of Bernoulli's equation. And since the thickness of the boundary layer is very small, there is no change in pressure with y. That is an assumption which is a valid assumption considering the small thickness of the boundary layer. So, I use Bernoulli's equation to find out what is dp star dx star. So, dp star dx star can be obtained, and for a prescribed geometry dp star dx star is a constant. For that reason, from the expression of del u star by del y star at y star equal to 0, which had otherwise contained dp star dx star, I can drop that, since for a given geometry this pressure gradient is known to me a priori and is a constant. So, in terms of functional form of the equation, whatever I have written over here can simply be written once again as del u star del y star at y star equal to 0 is a function only of x star and Reynolds number. I need not mention dp star dx star for a prescribed geometry. So, in other words, my del u star by del y star at y star equal to 0 is simply going to be f2, the unknown function x star times Reynolds number x star times REL. Now, when I use CF, which I have seen to be equals 2 by REL del u star by del y star at y star equals 0, which I have seen in here. This is where I have obtained the expression for CF. So, my CF is simply going to be 2 by REL F2 of x star and REL. So, my CF therefore would be 2 by REL F2, the yet to be evaluated functional function of x star and REL. So, these are the two equations that one needs to take a look at. First of all, u is a function of all the independent variables, the operational parameter and the pressure gradient. From there, I obtained the shear stress. From the shear stress, I obtained CF, and from del u star by del y star at y star equal to 0, I obtained the functional form for this special case when the geometry is known to me. So, this would give me the expression for CF for flow momentum transport inside a boundary layer. Now, let us see what is going to happen to the temperature profile. So, if I look at the temperature expression over here that we have obtained, my temperature profile T star would be a function of u star, x star, v star, y star, Reynolds number and Prandtl number. But this u star and V star are already a function, are already a known function of x star and y star and so on. For example, in this expression itself, what we have seen is that u star is a function of, once you specify x, y, Reynolds and dp dx, u star is specified. So, in the governing equation here, you do not need to write T star is a function of u star, because the moment you write T star is a function of x star, y star and Reynolds number, you essentially specify u star. So, by incorporating u star once again in your functional form, that would be simply a repetition. So, therefore, based on the knowledge of this governing equation, one should be able to write the functional form T star to be equal to a function f3, and I put it as x star, y star, Reynolds number, Prandtl number and dp star dx star. This dp star dx star, I am keeping it just as to make it complete, but we understand that for a prescribed geometry I can drop this dp star dx star. So, the same way I have done it for the case of shear stress, I am going to write the same thing for the case of surface heat flux, which I call it as QS. So, if this is the solid plate, you have the profile and you have flow taking place. I am trying to find out what is the surface heat flux at y star equal to 0. So, the surface heat flux is K, thermal conductivity of the fluid, times del T by del y at y equals 0. So, that is the Fourier law equivalent, that is the Fourier's law, in which can be expressed as minus K f del T del y at y to be equal to 0 divided by T s minus T infinity, and this is going to be equal to h, because my Q s, this is the equality of conduction and convection at this point, at the point where the liquid molecules due to no slip are stuck to the solid. So, the heat transfer from the immobile liquid molecules to the mobile liquid molecules, there you have the conduction and convection equality. So, this Qs can be expressed in terms of Fourier's law. This Qs can also be expressed in terms of Newton's law, which is h times Ts minus T infinity. So, h times Ts minus T infinity is also equal to, so these two are simultaneously valid at y equals 0, and therefore, the expression for h can be obtained in this fashion. So, when you express it in dimensionless form, this becomes h is equal to minus k f by L T infinity minus T s by T s minus T infinity times del T star by del y star at y star equals 0. So, this gives, I am slowly moving towards the dimensionless form of the expression over here. So, when you do that, when you cancel the numerator and the denominator, what you would get is h is equal to K f, the thermal conductivity of the solid, times del T star by del y star to be equal to 0, or in other words, you can write H L by K f is equal to del T star by del y star at y star equals 0. So, what is H L by K? This is nothing but the Nusselt number. So, we in convection, we always try to find what is H or what is the expression for Nusselt number. So, now I write a Nusselt number is I have used up F1, F2 and F3 over here. So, Nusselt number is del t star del y star at y star equal to 0. So, when I say it is del t star del y star at y star equal to 0, that function should be a function of x star, Reynolds number and Prandtl number, provided the geometry is known to us. So, thus this Nusselt number expression would be some function f4. I do not know what this f4 would be, but some function of x4, Reynolds number, sorry, x star, Reynolds number and Prandtl number. So, this is obviously for a prescribed geometry. Okay. And if you would like to find out what is the average value of Nusselt number, length average value of Nusselt number, the moment you do that, the length average value of Nusselt number, then x star is obviously dropped. It should be another function f5 REL times PR. So, this is the local value of Nusselt number, this is nu x, and this is the, so this is local value of Nusselt number, and this is the average value of Nusselt number, and the bar over nu simply denotes it is the average value, which is a function of this, and for length average value it would simply be a function of Reynolds number and Prandtl number. Now, when we use the Reynolds condition, Reynolds analogy, what I see is that dp dx is 0 and Prandtl number is equal to 1, and if that is the case, then the expression of u star and t star must be identical. This is what we were discussing so far. So, the expressions of u star and t star must be identical. So, what is the expression of t star and u star? So, u star is f1 and t star is f3. So, if your Prandtl number is equal to 1, the equation becomes dynamically similar. dp dx is the dependence of dp dx is not there. So, therefore, f1 must be equal to f1 and f3. f1 and f3 are going to be identical. Okay. So, f1 and f3 are identical. It is also then true that the expression for the friction coefficient, which is this f2, must also be equal to the f4, which is the relation for this case. So, expression for u star and t star must be identical would simply give you that f1 is equal to f3. Okay. And true also for friction coefficient and Nusselt number. So, if it is true for friction coefficient and Nusselt number, what you would get is f2 is equal to f4. So, these are collectively known as the Reynolds analogy. The important point here is the major problem that one would face in the practical application of Reynolds analogy is the requirement that Prandtl number has to be equal to 1. Whether you are going to get a fluid whose Prandtl number is equal to 1, and if it is equal to 1, how are you going to use this analogy for other cases? So, if f2 is equal to f4, how does that help us? f4 is this, f4 and f2, if these two are identical, if f2 and f4 are identical, I will write these two equations once again to show how we can use them in this case. Okay. So, Cf is 2 by R E L del u star by del y star at y star equal to 0, and we understand that del u star by del y star at y star to be equal to 0 is equals f 2 x star times Reynolds number based on length. And for the case of Nusselt number is simply equal to f 4 x star R E L times Prandtl number. Okay. So, if f 2 and f 4 are equivalent, then what we can say is that Cf from here times R E L by 2. So, Cf times R E L by 2 is this, which is f 2, must be equal to Nusselt number. So, if f 2 and f 4 are equivalent, then Cf times R E L by 2 must be equal to Nusselt number. So, this is known as Reynolds analogy. This is to some extent, in some cases it is modified in a slightly different way, where it is written that Cf by 2 is equal to Nusselt by Reynolds number based on length. And since the value of Prandtl number is equal to 1, there is no harm in adding a Prandtl number in this case. I can do that since Prandtl number in Reynolds analogy is equal to 1. So, this Nusselt by Reynolds into Prandtl has a special name which is called Stanton number. So, I can use Stanton number, I can introduce Stanton number since the value of Prandtl number is equal to 1. So, the more general form of Reynolds analogy is Cf by 2 is equal to Stanton number. This is the commonly used form of Reynolds analogy. So, this connects the key engineering parameter of Cf in fluid friction with H or Nusselt number in convective heat transfer. So, I would also like to draw your attention to the previous slide that I was showing. Nusselt number is equal to del T star by del y star at y star equal to 0. This again reinforces my statement that the significance of Nusselt number is nothing but the dimensionless temperature gradient at the solid liquid interface. So, that could be the definition of Nusselt number. The important one is the Nusselt number contains H. This is an engineering parameter, and here I connect Nusselt number with Cf friction coefficient, which also is an engineering parameter. So, through the use of this analogy, I connect the heat transfer with momentum transfer. But there is, as I understand, there is a problem that it is only valid for the case when Prandtl number is equal to 1. So, therefore, in order to extend the validity of Reynolds analogy to situations, to fluids whose Prandtl number may not be equal to 1, a correction factor is added to this analogy, and then it takes the, it is called the modified Reynolds analogy, and it is also known as the Chilton-Colburn analogy. Okay. So, to extend the Reynolds analogy, a correction factor is added to this as Stanton into Prandtl to the power 2 by 3. So, this is the correction factor which is added, and Stanton Prandtl to the power 2 by 3 is Nusselt by Reynolds into Prandtl to the power 2 by 3, and this extends the Prandtl number to a large range of Prandtl number. So, what you get then is Nusselt by Reynolds into Prandtl to the power minus 1 by 3 is equals Cf by 2, and this whole thing Stanton into Prandtl to the power 2 by 3, this is called the Colburn J factor. So, this is the expression for modified Reynolds analogy or Chilton-Colburn analogy, and the validity of this is extended in most of the real systems, real fluids, they have Prandtl number in this range, except for heavy oils which has Prandtl number more than 60, and the other extreme is liquid metals which has Prandtl number way below 0.6. So, for heavy metals, liquid metals and heavy oils, if we exclude these two special type of fluids, most of the liquids, most of the fluids that we ordinarily come across would be in this range, and therefore, the Chilton-Colburn analogy extends this for a wide range of Prandtl number. The advantage, what is the advantage? The advantage is, as I mentioned, Cf expression is already known to us, Rex to the power minus 1 by 5. Put it in here, and what you get is an expression for Nusselt number as 0.029 Reynolds to the power 4 by 5 into Prandtl to the power 1 by 3. The range of validity between Prandtl number 0.6 and 60. See the beauty of it. This is something which is really interesting. You have got an expression for Nusselt number. You have got an expression for H by simply using an analogy which has solid foundation. So, the expression for Cf is known to you. You are looking at the governing equations, non-dimensionalizing the governing equations. The similarity parameters are clearly obtained out of this exercise. You look at the dimensionless boundary conditions, see under which condition these two equations, governing equations, become dynamically similar. The moment they become dynamically similar, the solution of one can be used as the solution of the other. So, del u star del y star at y star equal to 0, which is connected with Cf, can be substituted by del t star del y star at y star equal to 0, which is connected with Nusselt number. So, the gradient of velocity or the gradient of temperature, all in dimensionless form, one related to Cf, the other is related to Nusselt number. The moment you make them dynamically similar, these two gradients are identical, and what you have then is an expression for CF and an expression for Nusselt number. The expression for CF is already known to you, therefore, you obtain an expression for the Nusselt number in turbulent flow. So, without getting into the complicated statistical analysis of eddy formation, velocity distribution, unknown velocity distribution, the fluctuations in temperature and in velocity, you have a tool now through the use of an analogy and an extended analogy. By incorporating Prandtl number corrections, you now have the expression for convective heat transfer coefficient in turbulent flow. That is the beauty of this analysis or this analogy. So, Reynolds analogy or modified Reynolds analogy, which is also known as Chilton-Colburn analogy, is a powerful tool which lets you find out the expression for H in highly turbulent flow. So, now I have the complete picture in heat transfer, external heat transfer, flow, the heat transfer in external flow. Simplest possible example, flow over a flat plate. I have an expression for H in the early part where the flow is laminar up to a value of Reynolds number 5 into 10 to the power 5. And through the use of analogy, I have an expression for the Nusselt number beyond Reynolds number 5 into 10 to the power 5, that means when the flow is turbulent. So, together they give me a complete picture of what would be the heat transfer coefficient in laminar flow and what would be the heat transfer coefficient in turbulent flow. More importantly, this I would show you in the next class. A corollary of that is a flow is never fully turbulent and the flow can change from laminar to turbulent. So, in most cases any flow has a turbulent portion to a laminar portion to begin with and then it becomes turbulent. So, those kind of flows are commonly encountered, they are known as mixed flow. The early part it is laminar, later part it turns turbulent. So, how these relations can be modified to express the average heat transfer coefficient for the case of mixed flow, but there is no new concepts are involved there. What is important is again I would bring your attention to this equation, which simply gives you the Nusselt number for the case of turbulent flow as a function of Reynolds number and as a function of Prandtl number. I should mention, as I was telling you, this is when the flow is turbulent from the beginning. So, when the flow is turbulent from the beginning, this expression can be used to obtain the value of H and so on. But in most of the cases, the flow is laminar to start with and then it turns turbulent. Those kind of flows are known as mixed flow. So, I will give you the expressions for mixed flow based on the expression of Nusselt number in laminar flow and in turbulent flow in the next class. But however, I would once again write the Nusselt number for the case of laminar flow, which just to compare them is 0.332 RE to the power half into Prandtl to the power 1/3. So, this is for laminar flow and this one is for turbulent flow. So, together if I combine this and this together, what I get is mixed flow, but this is obtained almost completely analytically. This has some approximation built into it, but it gives us the analogies give us a powerful tool to convert heat transfer data from the momentum transfer data, obtain an expression for heat transfer and vice versa. So, we will solve quite a few problems on this to clarify the concepts and to show you how this analogy can be effectively employed in problem solving.